Test. All right, folks, we're going to get started. Hope everybody had a lovely lunch. In an effort to keep us on time, I'm going to introduce Meng, who will be giving a keynote this afternoon on the Velox IO layer. Thank you, Meng.
Hello, everyone. So I'm Meng from the Metas. I'm a software engineer on the Velox and Presso team, and we focus on the recommendation system support. And today we'll cover the recent advancement we made into the Velox IO layer. So including the Nimble file format extension for the training data normalization solution at Meta, and also the recent open file format support for the Meta internal open data lakes efforts. So here is the agenda of the talk. First, we will give an overview of the Nimbles and how its current state in Meta. And then we talk about the extensions we made to the Nimble to support the training data normalization and Metas. And then we talk about the user sequence normalization and how Nimble help to improve the serving efficiency. And next, we talk about some of the new index types we're building into the Nimble file format. And then we talk about the I/O optimizations for the interactive workloads optimization. And last, we talk about the open file format efforts and our vision for Velox-based open data lake foundations and the current working progress. So Nimble is the high-performance column file format built at Metas. So initially built an ML workload, and currently we are kind of cover the interactive workload as well. So today, 80% of the training data and roughly 40% of the entire warehouse data is stored on Nimbles. And we roughly see like 10% of the storage footprint reduction and 10% of CPU efficiency on serving side, on training side. So Nimble is the fully open source, and compared with other open source file format, we have what's the difference? We actually have three differences. First, Nimble supports custom encoding, so we allow the recursive nested encoding. So for Parquet, for each column, we can only pick out one encoding type. But for Nimble, for example, if you choose wrong-length encoding, for a column, it will produce two substreams. One is value streams, the other is the wrong-length streams. For the value stream, you can first apply the delta encoding, and on top of that, you can recursively apply the var int encoding. For wrong-length encoding, you can choose the bitpack encoding. So each substream can choose its own encoding to optimize the data patterns to maximize encoding efficiency. The second is the encoding selections. So during the write, Nimble collect data statistics like the min, max, and the unique count. And then for the list of the candidate encodings, using the estimated encoding size and the weighted decoding speed, and to calculate a score to pick up the lowest the encoding with the lowest cost. And the third is that we are building the cluster index into the Nimble file format to support the key-based data skipping. And Nimble file format itself is extensible, so you can add a new index and encoding without modifying the core file format. So next we'll talk about the recent extension to the Nimble file format to support the training data normalization. The first Nimble Serializer. So Nimble Serializer is the serialization protocol. It converts a Velox vector into a Nimble encoding byte stream. And it's the wire format for network transportation and serving. And it has the three main components. One is the serializer, which is the convert the Velox vector into the serialized bytes, and then the deserializer, which is do the reverse. And then the projector we recently added to do the feature projection without decoding. So, and we also implement three key features to enable this. So first, we added the flat map encoding into Nimble Serializer. So with flat map encoding, each feature is independent stream. So do the feature projection, we basically just selected the byte streams without decoding. And the second, we integrate the Nimble Serializer with the Nimble encoding framework. So this allows per feature encoding selection and customization. And third, we added the coroutine-based parallel decode optimizations, which can significantly reduce the wait time and the client side and with minimal CPU overhead. So next one, we'll talk about the cluster index. Cluster index is a value index. It provides a key-based stripe pruning and row range, stripe and row range prunings. It requires data to be sorted and using three levels of binary search. At the first level is search, at partition level is search partition key to find what the key locate in which partition. And then once we locate the partition, we do second level binary search to find which chunk in the partition have the key. And then at the row levels, we decode the key stream and using the string comparison to locate exact rows. So we also provided the key encoder. So key encoder can encode a composite key index column value into a byte stream which is string comparable. So other than the training data normalization, class index can also help the two use case query access patterns. So first, just for the regular scan, we automatically to convert the filter on the index column into either the pointer lookup or the range scan. For example, if the query has a val clause, say the user ID equal to 123 and the timestamp is greater than a certain data range, we will convert it to the index bounds with the upper bound and lower bound. And then during the scan, we can just filter pruning the stripe and the row range and only to decode and load and decode the matched row ranges. So cluster index can also help the index join to do the batch index lookup against the warehouse table with Nimble cluster index. So we stored on the remote storage. And currently we have finished end-to-end integration with Presto for that. So next one is the chunk index. So chunk index, the position index, is provided from the row to chunk mappings. So it requires no data sorting. It decoupled from the cluster index. It can help in the two workloads. First, it can be used with cluster index. So cluster index is the map from the key to the rows, and the chunk index map the row to the chunk, so that we can directly jump to the chunk without sequential decoding. It can also help the filter push down, so we can skip decoding the chunks which doesn't match the filters. So then we talk about how the Nimble file format can help the training data normalization. Before that, we first talk why we do the training data normalizations. So in methods of modern AI training, kind of using the larger user sequence and the longer sequence and the long retentions. So these all cause exponential growth of the training data storage. And the problem is that the training data is denormalized. So the same user sequence got replicated across multiple training samples. The solution is the training data normalization. So basically, we extract the duplicate user sequence into the extendable, indexable storage system like REST-DB and ZB. And then when DBP, the method internal training framework, do the trainings, they will join the user sequence from ZB through the user ID and the time range from the training sample, and then merge with other remaining features to reconstruct a complete training samples for trainings. And we also, for the warehouse interoperability, we also replicate the normalized training data in warehouse and provide queryable through the Velox join algorithm, like index join, hashi join, and submerge join. It depends on what kind of workloads. So now we talk about how the Nimbles help the training data normalization to improve its efficiency. We currently partner with the ZB and the RexDB team to do the rollout in the two stage. In the first stage, we call it the Nimble, hybrid Nimble ST file, hybrid Nimble format. In this format, the data is still using the SD file format, but the value is using Nimble Serializer to decode. With the Nimble Serializer, we allow the ZB to do the fine-grained feature projection server side. So the projector we built can do the feature projection on the serialized value we read from the SD file. And then the benchmark result shows that we can reduce the projected bytes we sending from the ZB server to the client. And the client side, we optimize the decoding, so we see the signal reduction on the CPU time and word time. This stage, the benefit of this stage, we don't need any kind of infrastructure change to the DB server. And it can help to quickly unify the fragmented custom encoding into one format, Nimble encoding format. The second stage after this is the kind of end state to replace the entire SD file with the Nimble custom index file. So then we will have one file format for both training and the analytical queries. The column file formats can give us additional benefits on I/O efficiency through the fine-grained per feature I/O projection. To minimize the server-side CPU cost, we were using Nimble Serializer to pack the projected feature streams at a stripe level and keep the encoding all the way from the disk to the client side. So to minimize the overfetched rows, we're using the user-aware striping. So because each query is only for a single user, so user while striping ensure that for each stripe, it only contains the user sequence for particular users. And then the cluster index can exactly locate the exact row range. So the client side will only decode and match the rows. And the preliminary results shows that for the user sequence with range scan, the column index solution can be performed much better than the LT file format. Next, talk about some of new index we are currently building into the Nimble file format. So we have built a dense index. So this index is using the hash table to look up the key. So when the key comes in, first calculate hash for the key, and then based on the hash, we locate a bucket, and within the bucket, we do the key comparison. So this index doesn't require data sorting. When we're using Nimble in some of the, staging layer, which need a faster file injection, so we don't have to pay the data sorting cost like SD file form or Nimble cluster index file. And also, we provide optional per file Boolean filters to quickly check whether the key is in the file or not, so that if it's not exist, the entire lookup can be skipped. The hash table index itself can be partitioned and load on demand. So since we don't require the data to be sorted, so each file can have multiple such index with one per each different column index. So the other index we are exploring is vector search index. We follow the similar approach like Lens to embedding the vector index into the Nimble file directly. By co-locating the file and the index, we can always ensure they are consistent, and also one index for file format can be used by different query systems. Next, I'll talk about some of the optimizations we plan for to improve the entire warehouse workloads with the Nimble, like the selector reading and index-based data skipping and the encoding tuning. We plan to improve in the following 3 areas. First, we plan to modernize our I/O stacks. We are moving toward the co-reading-based async I/O for the lightweight CPU scheduling and the high concurrent workload. And we will continue investing in I/O coalescing, like merge small read into larger one, but still kind of try to avoid the excessively old reads and the highly selected interactive workloads. And the third is we integrating with the Sally cache for the local and remote flash acceleration. So Sally is the Meta's internal cache solutions. The second area is the encoding improvements. The first, we are seeking for the better encoding selection. One is to allow users to specify the custom cost function based on data patterns. The other is the ML assisted offline encoding selections for training data. So the other is the encoding exploration. There is a use case that they try to normalize the dense features. For that kind of use case, we have to use column format. But the query pattern is the pointer lookup, which means that we need to support very efficient SQL encoding to fetch the single values without decoding entire block. And the value could be a scalar value or the nested value. The other will continue looking into the whiteboard encoding. Like for current string types, we only support the generic string comparison. So we are looking for explore some encoding like FST, so that find a good balance between the encoding efficiency and the decoding speed. The last is the file format extension. We are currently adding the dictionary sharing and the dictionary encoding preservation cross-chunk and streams to reduce the story, I/O, and the memory cost. We also try to exploit the cross-stream similarity to avoid the data duplication cross-stream for some training data use case. And we are currently adding the fine-grained stats to enable the filter pushdown at both the stripe and the chunk level. The last, we'll talk about the recent open table format support. So the industry currently have converged on the modern open file format like Iceberg and Paimon. So Iceberg is the leading standard for the batch analytic, and Paimon is kind of emerging standard for the streaming read and the near real-time batching. So compared with the legacy Hive table format, those modern open table format has the following key capabilities. So one is manifest-based metadata, which include the partition spec stat and the per file tracking and the file stats, which we can allow the query system to do the query optimizer to do the multi-level partition, like partition level and the file level prunings without slow folder listing and footer parsing. The second is the manifest file-based immutable snapshot mechanism. The architecture-wise is easy to support ACID transaction and time travel and incremental query processing. The third is the filter ID based schema resolution is safer than the Hive. In Hive, it maps the columns based on the ordinal position in the schema. So whenever you use a drop columns or reorder columns, it will breaks. But in the Paimon and Iceberg, they assign unique field ID to the columns and never used, so it's safe to do drop column or reorder columns. And third is partition evolution without table rewrite. In Iceberg, the partition value is dynamic calculated based on the partition spec and the column values. So whenever there is a partition change, the metadata record the old files partition spec and new files partition spec, and the query abet know that will generate the remaining filters for the old partitions. Even though they're not very efficient, but it's better than the Hive. In the Hive, have to rewrite entire tables because Hive partition is fixed value, is part of the schema columns. So due to those reasons, so Meta internally have a couple efforts try to adopting those open table formats, including both Iceberg and Paimon. So why does this matter for Velox? And Velox is the shared execution layer. So we have one connector implementation will benefit all the query system built on top of the Velox like Presto, Sprout, and DPP. And then it eliminates the per engine integration cost. So our mission is kind of to build the foundation layer for the open lake solution, both inside Meta and outside Meta for the open source community. So the foundation spans three layers. On the top is the Axiom, which is query planning. So Axiom will understand the open file format metadata, will do the partition and the file levels filtering, and also do the speed generation to create working unit for execution nodes to execute, and also associate the deletion and do the deletion file and deletion vector associations. So the end goal for the Axiom is to unify the open table partition integration. So once we implement on the Axiom, all the query system built on top of Axiom will directly benefit from that. So Velox is provide a vectorized query execution and connector abstraction interface. So different query system on Velox can get a consistent read-write behavior through the connector. And this layer requires is performance critical. For example, for the merge read, it requires efficient to load the deletion vector into memory and then filter out the deletion rows efficiently. And all these are kind of optimizations and functionality can share across different open table formats through the connector utilities. So for example, both Paimon and Parquet has the deletion vector support. Meta internal Meta Lake also has deletion vector support, so they can all share the same optimizations. The last layer is the bottom layer is the storage layer. So we use Nimble to do the physical data storage, and we can leverage Nimble's extensive encoding and index capability to optimize the physical I/O performance of open table file formats. And the Nimble is fully open source, so our goal is to position Nimble as one of the supported open file format for those open table format, like other than the Parquet and ORC and the Lens. Yeah, so last is a quick update of the current connectors stats. So for Iceberg, we have feature complete and to the V3 versions. And on read side, we support predict pushdown, column pruning, and feature ID-based schema evolution and deletion vector handling. On the right side, we support writing data file writing and deletion vector generation libraries. And we next step, we will kind of tune this kind of performance in Meta use case, and also adding the support for Nimble file format, like the adding the field ID schema management inside the Nimble file format. And we're also working with other Meta internal infrastructure team to adapt to the Meta infrastructure for store integration and replication. For Paimon side, we currently actively adding the basic read-write support for append-only table for the initial near real-time use case at Meta. We also welcome the community to adding the primary key-based support if you see how the use case. The other thing to mention is that the ZB team in Meta is building the streaming lake solution called Flux. And so basically the more recent data is the new data is written through the SE file, and then the old historical data, they compact into the Nimble columnar file format with the class index. They built the Flux reader connector in Velox and provide transparent access to both type of file in Presto query and Spark queries. Yes, that's all I have. Yeah, thank you.